Okay, hi everybody. Thank you for sticking around for the second session of the high-dimensional expander workshop. We're going to start with Rachel, and she'll tell us about explicit lossless expander, vertex expanders. So Rachel, floor is yours.
Okay, test. Okay, great. You guys can hear me, right? Okay. Yeah, so I'm going to tell you guys about a new construction of vertex expanders today. I know this workshop is on HDX. So I guess before we get there, we're just going to talk about the X. So yeah, let's get started. Let's see, how does... Okay, cool. Is there also? Maybe here. Maybe it's not turned on. Sorry, technical difficulties. It's turned on. Okay, there we go. Okay, great. Yeah, so this is joint work. These are two works with my amazing co-authors. Okay, great. So first of all, just like high level, what is an expander graph? Max did a really good job yesterday of introducing the notion, but let me just say a little bit more. So an expander is a graph that is both well-connected and sparse. Well-connected means it should simulate the properties of the complete graph, but you want to do so with much lower degree than the complete graph. Okay, how do you formally define this mathematically? Well, there's a bunch of different ways you could define it. Here are maybe the three most common ways. And each different definition will lend itself to like different applications. So the three most common are probably vertex, spectral, and edge. Just very briefly, so vertex will be the one we're going to talk about today. And it refers to the notion that every small set of vertices should have many distinct neighbors. Spectral is going to refer to the notion that the second eigenvalue of the adjacency matrix is much smaller than the first. And edge expansion is going to ask that every set of vertices has many edges leaving the set. Yeah, so they have different applications. And also we understand the different notions to different levels of we understand the different notions in different ways. So like for instance, for spectral expansion, we actually have optimal construction of these items. So we understand it pretty well. And as a corollary, we also understand edge expansion pretty well. Like so there's so I guess spectral will give you good edge expansion up to lower order terms. On the other hand, with vertex expansion, the relationship is a little bit weaker. So spectral expansion will give us some weaker form of vertex expansion, but it won't give optimal parameters. So I guess to summarize, like out of the three notions of expansion, maybe vertex is kind of the odd one out. Like it's the one that we understand least in terms of how to construct it explicitly. So that's also the focus of today's talk. Okay, so I guess before I get a bit more into just exactly what vertex expansion is, let me just say there's a bunch of applications also. Okay, so what is vertex expansion? So we say that a graph is a vertex expander if every not too large set of vertices has many neighbors. Okay, so let's say we have a D-regular graph, D a constant, and you have a set S of vertices. It has D times S edges coming out of it. Ideally, you'd like these to hit as many different neighbors as possible. So we can define the quantity expansion of S to be the number of neighbors of S divided by D times S. So this is the number of neighbors of S over the number of edges leaving the set S. Right, so ideally, this would be as large as possible, close to 1. So 0 is very bad, 1 is very good. And we will say that the graph G is a lossless expander. Its expansion of every set S is at least 1 minus epsilon for every set S of up to like a linear size. So here eta is like the bound on the size of the set S. You should think of eta as a small constant. It can depend on the degree D. In fact, it will always need to be at most 1 minus 1 over D to even get vertex expansion at all. So, cool. So what do we know about vertex expanders? So first of all, random graphs do achieve lossless 1 minus epsilon vertex expansion. Okay, but what about explicit constructions? So, okay, so why do we care about explicit constructions? Well, first of all, it's a nice mathematical question, right? Maybe for those of you who do like more complexity, maybe you care about de-randomization. So it's a very natural de-randomization question. But besides just like the mathematical interest, there's also some other reasons you should care about explicit constructions of these items. So first of all, it turns out that there's likely no efficient certificate for certifying that a given graph has good vertex expansion. So even though you can generate a random graph, and with high probability it has lossless expansion, we don't know how to show that it actually does have good vertex expansion. Secondly, random graphs actually lack a lot of structure that you need for applications, whereas for explicit constructions, it often comes with more structure that you can actually use in your desired applications. So for instance, in this new construction of quantum LDPC codes, you'll need your loss expanders to also have a nearly transitive group action, which is not known to be achievable by random graphs. Okay, so we want explicit constructions of these items. What is the best we have? Well, I already told you that there is some vertex expansion you can get from spectral expansion. So let's talk a bit about that. So let me just remind you what a spectral expander is. A spectral expander is a graph where the second eigenvalue is much smaller than the first. The top eigenvalue is always going to be d, the degree of your graph. The second one, you can hope to be much smaller. So if it's very small compared to d, then we'll say your graph is a good vertex expander. It has many useful properties, and we also know how to construct them in many different ways. Okay, so what kind of vertex expansion do we get from these optimal spectral expanders? So if we have an optimal spectral expander, which is called a Ramanujan graph, Kahale showed that this will actually give you 1/2 vertex expansion. Okay, on the other hand, can you do better? It turns out for Ramanujan graphs, this is actually tight. We don't know any Ramanujan graphs that can do better, and we actually know Ramanujan graphs that get exactly 1/2. So in particular, the property of spectral expansion by itself will not imply the property of strong vertex expansion, just as properties alone. So let's add to our chart. So we said that optimal spectral expanders will get you 1/2 vertex expansion. This was what we're going to call a spectral barrier. It turns out this is also the best we knew up until like last year. Yeah. And so it's been a question for like many years of how you can beat this 1/2 spectral barrier. And in fact, if you were able to beat 1/2, you could also get some extra applications. So if you can beat 1/2 by any amount, you can get good error correcting codes. In fact, you only need something weaker called one-sided vertex expansion, which we already knew how to do, but nevertheless, beating 1/2 is like it does actually give you new applications. And then more recently, there's a work of David and Min, who showed that you can actually get good quantum LDPC codes if you get 11/12 vertex expansion. So if you get like almost lossless, but not quite, like you can get new constructions of useful quantum codes. That we did not know how to achieve via loss expanders before. I also want to mention that there have been weaker variants of vertex expansion that have been studied. So one version of note is what's called one-sided lossless expansion, which is where you have a bipartite graph and you only require vertex expansion from the left to the right. So you have no requirements on the right to the left. There's also been a study of what's called unique neighbor expansion in an unbalanced setting, where maybe the left side is much larger than the right side. And also, if you only want expansion for very small sets, like maybe not linear sets, but much smaller, like small polynomial or even subpolynomial size sets. All right, so that's what we know. What do we show? So in the first work I mentioned, we pushed past the spectral barrier and got 3/5 vertex expansion, so beating the spectral barrier for the first time. And in our second work, we push it all the way up to lossless, so we get 1 - epsilon. And special note, our expanders have the special group action I mentioned before that will get you quantum LTPC codes as well. Okay, let me just say a couple more words about our results. So more generally, we prove that we can construct graphs of this following form. Our graphs are going to be bipartite. You can even support slightly unbalanced degree. So you can get C by D by regular graphs with a property that every set on the left will expand to many neighbors on the right, and every set on the right will have many neighbors on the left. All right, but maybe today we can just stick to like both sides that have equal degree. So maybe both sides have degree D. Okay, any questions so far? I know this is a very large room, so it's like kind of awkward to ask, but feel free to stop and ask questions since you have any. Cool. So if there's no questions, then maybe I can tell you a bit more about our constructions. So let me start with a high-level strategy. So first of all, the first observation we're going to start with is the observation that random graphs are in fact good lossless expanders. As I said before, we can't just find a large random graph and verify that it has good lossless expansion. But what you can do is generate a small lossless expander, a small instance, via exhaustive search. So if you're only going to ask for constant size, let's say d by d, so d versus on the left, d versus on the right, we can actually find such graphs. Let's say we found such a graph, let's call it h. So this is going to be sort of our so we have this h, let's keep it in memory. We're going to come back to it. So what we're going to do now is we're going to implement a local to global strategy, where we're going to overlay the gadget graph h many times in some way, so that the resulting graph is much larger and will also have the same properties of lossless expansion the smaller graph does. Good. That's very high level. Maybe let me tell you a bit more about how we actually overlay the gadget graph h. So we do this via what's called a tripartite line product. So this tripartite line product consists of 3 sets of vertices. There's a left set, a middle set, and a right set. In the final construction, only the left and the right are actually going to be in the construction. The middle is just there to inform how the construction is built. So yeah, okay. So how is the middle related to the left and the right? Well, between the left and the middle, you just think of there being a graph GL, which is k by big D by regular. And similarly on the right, there's going to be a graph GR, which relates M to R, which is going to be D by K by regular. You should think of K as being much smaller than D. So maybe in your head, you can think of K as being like 4 or some smaller constant, and then D should be much larger, but still a constant. We're going to call the graphs GL and GR the base graphs of this construction. All right, so now given these base graphs in these 3 sets, we're going to introduce back our gadget graph. And the way we're going to place it on this graph is as follows. We're going to look at every middle vertex, look at its D left neighbors and its D right neighbors. And then we're simply going to place a copy of the gadget graph H on top between the 2 sides. Okay. And we're going to do this not just for one vertex, but for every vertex. Here I've just drawn it for 2 different vertices. The final graph we're going to get is going to be the graph with left side L, right side R, and then all the red edges. We're dropping M and GL and GR. It's just all the red stuff and then L and R. Okay, let's just count the degree just to make sure we understand what's happening. Let me see if I can get this pointer to work. I don't know how to make this work. Oh, did that work? Okay. Yeah, so anyway, okay, so if you look at any left vertex, let's say, well, it's going to have k different middle vertices it's adjacent to. So it's going to partake in k different gadgets. And each gadget graph is going to have degree rho dh according to the gadget graph. So the final graph we're going to get is going to be k times dh by regular. All right. Okay, so that's the overall idea. So I guess I've told you basically how the entire construction looks, except for what the base graphs are. So maybe let me tell you now what the base graphs are. So first of all, so in previous work, HMMP in 24 chose Ramanujan graphs to be their base graphs. They're optimal spectral expanders, the best spectral expanders you could hope for. Unfortunately, it seems like if you just use the spectral properties of Ramanujan graphs, of these one-dimensional graphs, it doesn't seem like that's going to be good enough to actually argue good vertex expansion. So that's just like my claim. We'll talk about it more later. So our observation or idea is going to be to use a base graph that also additionally has some higher dimensional structure. And we're going to leverage both the spectral properties and the higher dimensional structure to actually analyze our construction. So in particular, the base graphs that we choose in the first work is going to be the Ramanujan complex, the base graph based on the Ramanujan complex, which is one of the HDXs that Max was talking about yesterday. And using that, we're going to be able to get 3/5 vertex expansion. In our second work, we use a base graph based on the Ramanujan cubical complex. And using that, we were able to argue all the way up to lossless. Cool. Any questions? Yeah. Yeah, so yeah, it's a good question. So yeah, so L and R are going to be connected to M by these graphs GL and GR. And then yeah, I guess like for every middle vertex, you look at its left neighbors according to GL, its right neighbors according to GR, and then you place a copy of the gadget graph.
Next slide, you're talking about when GL is
Mhm.
Oh,
Yeah. Yeah. Okay. Yeah. So then that was the overall framework, and then this is the choices of base graphs themselves. Yeah.
so examples of graph with GL and GR and the result graph actually fail.
We'll get into it if we have time. So I think the answer is like kind of like the analysis will fail because we can't prove more things than the spectral properties give us. But then like it's conceivable it will still work. We just don't know how to show it. Yeah, I think in general, this entire challenge is like most of these graphs are probably lossless expanders, but we just can't show any of them are lossless expanders. So like that's really the challenge, is to come up with a graph with like a certificate of expansion, basically. So yeah. Oh yeah, okay. So the question was like, does it matter like how you assign the left vertices and the right vertices of the gadget graph? Like how like you actually like assign that in the GL and GR? And the answer is if you want the group action, then it does matter because you want the labelings to be consistent so that the group action actually like is consistent. Yeah, and it might matter in general, but I think that maybe the main reason is you want the labels thing to be consistent for the group action. Yeah. Yeah, if you just take Ramanujan graphs, it would be 1/2 vertex expanders, and then yeah, I think you can think of it that way. I think is it really a bad expander? It's like, is that just because like it's small degree or sure? But like if you exclude laziness, it's okay, right? Mhm. Yeah, I guess they're not gonna be Ramanujan, but like I think they are like near Ramanujan, or like up to like some constant or something. Yeah. Yeah, so I guess like the base graphs that we actually use won't have very good vertex expansion themselves. Like it'll be some really small constant, but then somehow like we just like the higher dimensional structures was really important for like helping argue properties we need. Okay, any more questions? These are all good questions. Okay, so maybe the rest of the talk, I'm just going to tell you about the second result. So this is a lossless result. And if you want to hear more about the first one, I'll be talking about it tomorrow during the stock program. So yeah. Okay, so the Ramanujan cubical complex, let me tell you what that is. So let's start with a one-dimensional case, because I think that's the easiest one. So a one-dimensional cubical complex is simply a Cayley graph. And for those of you who know what a Cayley graph is. What is a Cayley graph? Well, it's defined on a group, gamma, and also a generator set, let's say called A. You should think of A as being constant sized. And the one-dimensional cubical complex is going to consist of two copies of the group gamma as vertices. And then between the two copies, we're going to place edges according to the generators. So in particular, yeah, a group element G is going to be connected to all GA for A in your generator set. So notice that every left vertex has degrees the size of the generator set. It's also going to be true for the right side. You can take the inverses, but let's assume that maybe the generator set is closed under inverses. So A is equal to A inverse. So yeah, all these backward edges also exist. And so the other side will also have the same degree. In this case, I get 3 in the diagram. So that's just, yeah. So every vertex is contained in A different edges. Okay, so edges are going to be one-dimensional cubes. Okay, let's move on to higher dimensions, 2 dimensions. So here we're going to have this the same group gamma, 2 different generator sets, A1 and A2. The 2D cubical complex is going to be defined on 4 copies of the group gamma as vertices. In the horizontal directions, we're going to place generator set, like edges corresponding to A1. In the vertical direction, we're going to place edges corresponding generators in A2. Okay, so both the horizontal direction and the vertical direction are going to be Cayley graphs. Okay, 2 dimensions means we need more than edges. What is more than edges? Well, squares are more than edges. So it's also, so the 2D cubical complex consists of vertices, edges, and also squares. Squares are simply collections of 4 edges that, like, I guess, form a square in the complex. Great, and then you want these generator sets to satisfy a property to make sure that squares actually do arise. For most choices generator sets, like, you won't get squares. So how do you get squares? Well, you have to satisfy what's called the cubical property, which is the following property. So let's say you start at any group element G here in the bottom left. If you pick, okay, maybe I should send it back here. If you pick A1 and A2, which will take you to the left and the right, you want there to be a unique choice. Sorry, I'm going to emphasize unique. So a unique choice of generators A1 prime and A2 prime, which would take you, kind of completes the square into a square. So in particular, when I want the property is that for any A1, A2, there's a unique A1 prime, A2 prime satisfying A1, A2 prime is equal to A1 prime. Okay. So let's talk about degree. Yeah, so if you start with any element in the bottom left, G, there's capital A1 number of ways to choose the left direction, and capital A2 ways to choose the vertical direction. So the total, for each of these directions, a pair of directions, you can there's a unique way to complete the square, right? That's what the cubical property says. And so as a corollary, we'll get that every vertex is contained in A1 times A2 number of squares. I want to say, I said this all for the bottom left, but it doesn't really matter which side you start with. Again, we're going to assume that A1 is equal to A1 inverse and A2 is equal to A2 inverse. So it's really symmetrical no matter where you start. Okay, 3D. So we're just going to bump 2 up to 3. So we have a group gamma, generator sets A1, A2, and A3. And the 3D cubical complex is going to consist of vertices, so 8 different copies of the group gamma. In each of the 3 directions, we're going to have the Cayley graph corresponding to that generator set. And the cubes are going to be all the, I guess, all the cubes that arise in the graph, like every time you get some set of 12 edges, which are connected in this way. And the cubical property we're going to want is that for any A1, any generators A1, A2, and A3, there is a unique way to complete it into a cube. Cool. And similar to the 2D case, we can argue that every vertex is contained in A1 times A2 times A3 number of cubes. Okay, let's talk about this cubical property. Maybe let me go back to the previous slide really fast. Yeah, so the cubical property has this kind of like commuting condition. It's like semi-commuting because it's not really commuting, but like I guess like if you have an abelian group, it turns out this cubical complex is like trivial to satisfy, right? Because if you have A1 and A2, you can just pick A1 prime equals A1 and A2 prime equals A2. So then you satisfy the cubical property. But for us, we're going to actually want, but unfortunately for abelian groups, the smallest generator set is going to be of log size, and we're going to really want constant degree. So we're going to have to use some non-abelian groups for our construction. So in particular, we're going to use a non-abelian Ramanujan cubical complex due to Jordan and Livney in 2000 and also RSV in 19. This has a property that you have constant size generator sets, A1 up to AK. Also, between any 2 parts, like any 2 neighboring parts, the resulting Cayley graph has Ramanujan expansion. And we know how to construct these things using the LPS Ramanujan Cayley graphs. Turns out that if you pick the same group gamma and you pick different LPS generator sets, you will get such a cubical complex. Right. Any questions about the cubical complex? Yeah. like I think constant, or honestly even like root d plus like to the 1/2 plus epsilon is, sorry, d to the 1/2 plus epsilon is fine too. Yeah, there's like some looseness in the analysis, like you have some room for. All right. Let me, yeah. Right, yeah. I think you'll get like part way, but not all the way there with just the 2D. If you just know that you have like every pair of things is like a 2D Ramanujan cubical complex, you'll get like partially there, but you need like somehow to argue uniqueness, you need a little bit more than that. So I think the analysis really does go through like understanding the group of bit itself. Almost, because you would, if you use our construction, you would get explicit expander of degree log n, but, or sorry, it's not explicit because the gadget graph would no longer be explicit. You needed, I think, okay, maybe by log n, it really should be like log cubed or something. It'd be slightly super polynomial. Yeah. You lose in the size sets up too also, because if your degree is worse. There is a, okay, actually I'll talk about it in the next slide. Actually, no, I won't talk about it in the next slide. But okay, so let me just say. So there is a cubical complex in DLV that they do like the LTCs, like the QLTCs. And they do get constant degree, but you still lose in your set size. So I think you can shift around the log a bit. Like you can figure out if you can put the log somewhere else. But yeah, so let me compare it to other complexes in case you guys have seen other complexes before. So compared to the left-right Cayley complex, which was used in the breakthrough work of like constructing C3 LTCs or in QLDPC codes. Yeah, so theirs was only limited to 2 dimensions because they have like basically they use a left side and a right side for the generator multiplication. So you're limited to 2 dimensions. On the other hand, we're going to really require that our complex can get to any constant dimension. So that's not going to be good enough for us. There's also the cubical complex of Denier, Lin, and Vidic used for constructing QRTCs. They basically do the abelian version of our complex, and you get a log loss in parameters. Our complex, on the other hand, is k-dimensional, can be any arbitrary dimension k. It is constructed over non-abelian groups, and it will achieve constant degree. So best of all the worlds. So maybe now that you know what a cubical complex is, I can tell you what our base graph is. So let's say we start with a cubical complex. This is going to consist of a bunch of vertices and a bunch of cubes. Cubes are one vertex in every set with edges between them. The resulting base graph we're going to construct is going to be as follows. We're going to place cubes on the left and the right. The middle, we're going to place vertices, but not all the vertices. We're going to look at, let's say in this 3-dimensional case, these 4 sets of vertices chosen according to the Hadamard code. If you don't know what the Hadamard code is, that's fine. Just think of sort of equally spaced out sets of vertices. And then we're going to place these 4 vertex sets in the middle. Once you have, so we have cubes and vertices, we're going to connect them if the cube contains the vertex. And we're going to do that not just one, but for all. Okay. Any questions about this? Why Hadamard? Good, we'll get there in a bit. Yeah, okay, so let's just analyze the degree just so we are all on board. So if you look at the left side of these base graphs, these have degree 4 in the 3-dimensional case. Right, because there's like 4 different vertex sets that you can be connected to. From the middle to the left, you will have degree, like the question is like how many cubes is each vertex contained in? And we really analyze this to be A1 times A2 times A3. Similarly, on the right is going to be A1 times A2 times A3 by 4 by regular. In general, for general K, you're going to get K plus 1 and then the product again, and then K plus 1. Okay, so that's the base graph. Let me again remind you just what our final construction is going to look like. So once we have this base graph, we're going to use a gadget and place it on top of the neighbors of any middle vertex. So you fix a vertex, you look at all the cubes containing the vertex on the left and the right, and we're going to place a copy of the base graph between them. Let me move this bit. Okay. And then the resulting graph is just going to consist of all the red edges once you perform this operation. All right. So now let me answer your Tom's question. Oh, sorry. And yeah, this graph is k plus 1 times dh by k plus 1 times dh by regular. For the same reason I said earlier, each left vertex has k plus 1 left degree, and then so it participates in k plus 1 different gadgets, and each gadget has degree dh. Any questions about this? Okay, so maybe let me answer your Tom's question now, which is why the Hadamard restriction. And the answer is basically going to be that the analysis involves a delicate balance of parameters. And for the analysis sake, it's much easier if all these parameters are kind of like symmetrical. And what do I mean by that? So like in particular, if we restrict to the vertices of the Hadamard code, it symmetrizes the complex. Like note that the distance between any two vertex sets is exactly 2 in this three-dimensional case. You don't have any that are distance 1 from each other or any that are distance 3 from each other. So you really get a very nice symmetrical complex. Yeah, so like the reason like we were stuck to 3/5 in the, I guess in like the OSV complex was because like, there was too much imbalance at some point and we couldn't get around that. Okay. Are we all good right now? Okay. So let me talk about the analysis and I guess I have a lot of time, so that's good. Okay, so let's talk about the analysis. So let's start with the outline. So what's a high-level overview? So the goal is going to be to show that every set of vertices on the left has many neighbors on the right. So the way we're going to do this is we're going to analyze all the gadgets that S will participate in. What are all the gadgets that S will participate in? Well, there's going to be one corresponding to every single neighbor of S in the middle, right? Because we place gadgets on the middle vertices. And like a gadget will only have any edges at all if it's connected to S. So once you have the set of gadgets, U, we're going to split U into good gadgets and bad gadgets. So the good ones will be U low and the bad ones will be U high. Let me tell you why they're good and bad. So U high, let's start with the bad ones. They're going to be the bad ones. U high is going to consist of all the middle vertices that have many neighbors on the left in S. In particular, this can be bigger, has more than D over DH, many vertices on the left in S. So if you have a lot of neighbors in S on the left, then now imagine placing the gadget on these vertices. The gadget has degree DH, right? Your set size, your number of vertices in S is at least D over DH. So the number of edges you have kind of leaving S is going to be at least D. It's going to be bigger than D. But if you have bigger than D number of edges, well, there's only D number of vertices on the right. So they're going to have to collide a bunch of times, and you're going to kind of lose all your vertex expansion. So these are going to be the bad gadgets. These are the ones where there's not going to be any expansion in the gadget. Okay, the good ones are going to be the complement. So we call this U low. These are all the gadgets with few vertices on the left in S. And we will get a good lossless expansion in this case, just by the guarantee that we picked the gadget to be a good lossless expander. Okay. So now that we have these definitions, the analysis is going to consist of 2 parts. The first is we're going to show that most vertices in S have many neighbors in U low and very few in U high. This will mean that most of the edges leaving S will actually be good, at least within the gadgets themselves. The second step is like after you know that you have many U low gadgets, like many good edges within gadgets, we want to show that these gadgets themselves don't collide and cancel each other out. Yeah, so I guess like by canceling out, I mean that you have 2 U low gadgets, but they share a vertex on the right, then it's possible for the edges to hit each other and then disappear and basically not give you a unique neighbor anymore. Yeah. Yeah, that's a good question. So if you analyze one side, then you actually end up analyzing both sides, because you can imagine having a set that has vertices on the left and the right. What you can do is you can split it into the left and the right, analyze each separately, and then just add it together. To suffice it to just do one. Yeah, exactly, yeah. Okay. And then the thesis of the talk is basically that if you have strong spectral properties and you have higher dimensional structure, then analysis works. Okay, so let me try to convince you why, if you just have strong spectral properties alone, you won't be able to analyze the resulting graph. Okay, maybe I'm just gonna. Okay. So why doesn't strong spectral expansion alone suffice? So let's do an example. Let's show it by example. So our example is going to be the one-dimensional cubical complex as our base graph. So what does this mean? Well, on the left and the right, we're going to place edges. This is just a Cayley graph, so it's just going to have edges. And then the middle is going to consist of all your vertices of your Cayley graph. So in particular, like note that the left degree and the right degree of the left and the right is 2, because each edge has exactly 2 vertices inside of it. So this is an example of a base graph, which will have optimal like expansion properties, but it won't have any higher dimensional structure. And what I'll show you is that no matter how we choose a gadget graph, one of the 2 steps of analysis will fail. Okay, so when you choose a gadget graph, you have kind of 1 degree of freedom. You have the freedom to choose a degree dh. This is the degree of your gadget graph. You can choose it between 0 and d, where remember big D is like the size of your gadget graph, number of vertices in it. It turns out that if you choose dh to be bigger than root d, then step 1 will fail. How can step 1 fail? Well, it just means there is some set that won't expand, like it won't satisfy property 1. Okay. On the other hand, if you pick dh to be too small, then what we'll show is that step 2 will fail. In particular, there's going to exist some set that once you analyze it, you'll see there's too many collisions between different gadgets. So these 2 attacks, unfortunately, both have width exactly root d. They're going to meet right in the middle, and there's not going to be any range of parameter for dh that you're going to be able to choose to make analysis work. And it also turns out that both of these non-expanding sets are going to come from what we'll call small root d edge density sets that will exist in some Ramanujan graphs. What is a root d edge density set? Maybe let me just tell you like the property that we know can exist for Ramanujan graphs. So Kaufman and Camper showed that there are Ramanujan graphs and there are sets of vertices U, such that if you just like takes a restriction of the graph to just the vertices in U, there are root d edges like coming out of every single vertex. So I guess by edge density, I mean like if you look at a small set of vertices, that's like the average degree of the resulting graph. And the root d in the theorem is not, it's like there's no coincidence, it's not a coincidence as the same as like the size of the intervals. Like the root d there is exactly the same as the root d in the width of each of the attacks. All right, let me try to tell you the 2 attacks now. Let's start with the first one. So this is a case where dh is too large, and we're going to show that step 1 fails. Let me remind you what step 1 was. So step 1 was trying to show that you have many U low gadgets and very few U high gadgets. So the claim is that in the case that dh is too big, there exists a set S for which there are no U low gadgets at all. So let's define the set. So we start by keeping in our mind the set U that we said earlier, the root d edge density set. And we're going to define S as all the edges within the set U. Okay. So note that we said that U is a root d edge density set, which means that the average degree within just U is root d. But what is that degree? Well, it's also equal to like if you go from U to S to U, it's like that degree, right? Which is also just a degree from U to S. So in particular, you have the property that every single vertex in U has exactly root D neighbors in a set S. But if it has exactly root D neighbors in a set S, this is bigger than D over DH, because we said DH was very big. Definitionally, that means that every single vertex in U is actually in U high. Okay, and recall, U high are bad gadgets. These are the ones that don't have any expansion within the gadget themselves. Okay, so then that one is going to fail. Okay. Yeah, so this is just like a summary. So yeah, if you have DH too big, then because of this root D edge density sets, we're going to fail. Okay, does that make sense? Okay, great. Like 2 people are saying yes, so that's good. Any questions? Like, okay. Okay, cool. Let's do the second case, which is when DH is very small. In which case we're going to show that our step 2 of analysis is going to fail. Recall that these collisions are going to arise from collisions between different gadgets. Okay, so when can collisions arise between gadgets? Well, let's say that you have, okay, let's say you define your set S to be some set of vertices on the left, and U is going to be all the neighbors of S in the middle. Let's look at any single vertex of S. Sorry, let's look at any vertex U in big U, so that it has exactly one vertex in the set S. This vertex S, under the gadget graph, is going to have some number of neighbors, DH neighbors on the right. These were all originally unique neighbors, like good neighbors on the right. But you could have the property that there's another vertex in U, which will share that same vertex on the right, and it will collide out. So what we want, so in particular, the number of collisions that a vertex U could possibly experience, the number of collisions of like its right neighbors that it will possibly experience, is given by the number of U to R to U neighbors. Because like if there is to exist a vertex on the right, which could get canceled out, it means that from like the U to the right vertex back to the second vertex, there has to be a path. Okay. So in particular, if you want there to be expansion in the end, you're going to need DH to be bigger than this number of collisions. All right, but what is the number of U to R to U neighbors? Well, we kind of already talked about it, but for the left side, right? Like recall that the middle is just vertices, the right is edges. So we're going vertex to edge to vertex, which is simply just your normal degree of your set U. So this is exactly root D if U is a root D edge density set. Okay, so this attack will work whenever DH is bigger than root D. I'm sorry, whenever it's less than root D. So we'll need DH to be bigger than root D to work. So in particular, when DH is less than root D, this attack will work, and we won't be able to analyze step 2. Yeah, sorry, I think I messed that part up, so yeah. So just by the thing I've written up there, we'll need DH to be bigger than root D in order for this attack to not go through. Like, for our step 2 to work, we'll need DH to be bigger than root D. Yeah, so this is, I think, where like Sam asked earlier, if this is like constructive, and if you if it's always going to fail, the answer is probably not, because this is like not like your collisions aren't always going to coincide exactly with your neighbors, but you don't know how to analyze any other way. So like the best we can do is kind of a counting argument, or the best I know how to do is a counting argument. If you know better, you should tell me, because I'd really like to know. Okay. Just to summarize, so we have 2 attacks. One's going to work for the 0 to root D regime. The other's going to work for the root D to D regime. And both attacks are arising exactly from root D edge density sets within Ramanujan graphs. So our main idea is going to be to analyze, instead of analyzing simply edge density, we're going to analyze the density of higher dimensional faces. So in particular, in our base graph, the same 2 attacks, if you look at it for our base graph, the first one is still going to be related to edge density. The second one, however, we can instead argue it with tetrahedron density, or like a higher dimensional phase density. And that allows us to kind of like, it allows the attacks to actually have a gap between them. And there will be an interval for DH, which you can pick, which will allow you to successfully perform both steps 1 and 2 in analysis. All right. So I guess like I should tell you what edge density and tetrahedron density mean, because we're in a cubical complex, so it's not clear yet what that means. So let me actually tell you a bit more, which is like the simplicial view of the cubical complex. I think it's not written in our paper, but like I think it's a nice way to think about it. So hopefully this is useful for some of you who've already looked at the paper also. So what is a cubical complex? A set of vertices and a set of cubes. Cubes are going to be vertices, one from each of the sets with edges between them. Recall that we did this Hadamard restriction where we selected these Hadamard sets and then we dropped the rest of the sets. Once you drop these sets, what you can do is you can replace like you have these like red and green edges, right? You can replace it with like a single edge from sort of diagonally across. So you'll get sort of tetrahedron. So what we've really done is constructed a simplicial complex of some form. So cubes are going to turn to tetrahedron once you take this Hadamard restriction. So edge density now, as we're going to define it, is simply going to be sort of the average degree of when you restrict to a small set. So the maximum over all small sets of the average degree. So same as before. Tetrahedron density is going to be the maximum of like the average like tetrahedron degree. So the average number of tetrahedra each vertex in U is contained in when you just look at tetrahedron only in the set U. And then if we translate back to the cube language, this is going to be sort of like the number of cubes with all 4 vertices in your set U, like the average degree of that. Okay. So let's return again now that we know what edge density and tetrahedron density mean. Let's go back to the non-expanding sets, and let me try to tell you why this is like the right values to be looking at. So our first attack, so these were the ones that arose from collisions between gadgets. And we said in our earlier slide that the number of collisions that each vertex experiences is given by the U to R to U path. What is a U to R to U path? Well, it's a path from a vertex to a cube containing it to another vertex in the cube. And let's draw maybe it in the cube form. What this really means is you're going from a vertex to a cube back to a vertex, which is simply just an edge within the simplicial version. Okay, so that's why this is still edge density. The second value, maybe also let me say, so like in the Ramanujan case, when you analyze edge density, you always get to root D. So you always end up with an attack that extends halfway through this line. Interestingly enough, if you have higher dimensional structure, you can analyze this edge density to be much smaller. The reason is basically that there are much fewer edges than there are cubes per vertex, because there are many cubes per edge. The number of edges is just much smaller, and so if you're just looking at edge density as opposed to cube density, you'll get a much smaller value relative to the number of cubes in the graph. Okay, the second attack is the one that arises from sets S, which have many vertices within U. So in the Ramanujan case, we said that our attack set S is a set of all edges contained within a set U. And like the edge density, the number of edges like in the set U is what determines the width of this interval, this pink interval. Another way to say the edge density is the following question. It's like how many 1D cubes have both vertices in U? It turns out that if you ask the same question, but for higher dimensional cubes, you'll get another pink attack that extends exactly to the yellow bar and meets the yellow bar exactly. So that won't be good. But the nice thing about having higher dimensional structure is you have room to ask bigger number of questions. So in particular, if you ask the following question instead, how many cubes have all 4 vertices within U? You can actually get a smaller value. You can get so the pink attack will actually shrink. So that's kind of the reason why we can argue tetrahedron density instead of edge density for a second attack. So the final equation Yeah, so the final equation we're going to have is we're going to want the size of these two attacks to be smaller than the total length of D of D, which is the product of the A1 to AK. So you want, this is the product of the two to be much less than D. And what we're able to show is that the edge density is about D to the 1/4, and the tetrahedron density is about D to the 5/8. And if you product these together, you'll notice that there is still a D to the 1/8 gap between the two. So if you pick your little DH in this interval, then you'll have constructed a good lossless expander. Okay, so that's it basically. Were there any questions on any of the technical portion? Yeah. Yeah. So so the reason is going to be because like when you do like the first like step 1 of the analysis, you want to show that like most vertices have many many U low vertices and very few U high. And you do this by rolling out like, let's say, tetrahedrons. Like you're saying, oh, at most 4 of them can be in U high or something. So you need a number like the dimension like k to scale to be much larger than 4, so that you can like get closer to 1. Actually, I kind of lied when I said tetrahedron here, because in general, you're going to have to take like root k instead of 4. So like really the final expansion you're going to get is going to be 1 minus 1 over root k. So if you want closer to 1, you're going to have to take k to be larger. Yeah, the analysis is a bit weird because like in some sense, like the most of the where you get the gap is from tetrahedron, but then like when like higher dimensions, you basically say like, oh, let's say you have root k different neighbors within U, and then you can reduce it down to the tetrahedron case and then use that inequality. So it's like sort of root k and it's sort of tetrahedron, depending on how you look at it. Great. So I guess in conclusion, what we did is we performed a local to global sort of procedure where we took a small gadget graph. We combined it with a higher dimensional amplifier, and as a result, we got a large lossless expander. And maybe just like the thematic question for like the workshop in general is like, what other objects can you build using the same framework, using a higher dimensional structure as an amplifier to lift properties of local to global? Yeah, but I guess like also I just wanted to tell you some questions that came up during this research that I really want to know. So first of all, like there's this edge density question. For us, we were always stuck at root D because we don't know how to do any better for Ramanujan graphs. And in fact, if you just find an explicit graph with smaller edge density, it's very possible you could get alternative construction for vertex expanders, for lossless expanders. So that'd be really nice. So this is a question that's been like driving us nuts for a while now. So would love if you could give me any insight. Another question is like, I think the practitioners like for like, let's say coding theory or like other subjects really want like explicit loss expanders with like really small degree D, whereas ours is going to scale pretty quickly just because Cayley graphs already are pretty large. So I guess this is like really like the more like practical regime. Like, can you do it for like say degree 10 or something? And then also another question is like, what about the D versus like lossless trade-off? So the best we can hope for random graphs is like epsilon is about 1 over D. But even in the one-sided case, which is like the easiest, like which we've known for like 20 years now, the best we know is epsilon is 1 over root D. So it'd be really nice to beat that and get closer to 1 over D. And finally, like, I'd love to see more constructions of lossless expanders, or sorry, more applications of lossless expanders, because yeah, it's like we have this object now. I think it's pretty strong. What can you do with it? Yeah, and that's all.